This is part 1 of our lecture video series for Friday, March. Wait a minute, is it really the 24th? Oh man, it's the 24th, not the 25th. So we're going to begin with a warm-up that is some more practice for predicting precipitate formation in a double displacement reaction of aqueous solutions. So we have this problem here. Predict the products and identify any precipitate that's formed when aqueous potassium phosphate is mixed with a solution of magnesium chloride. So if we go through our process, we first need to start by writing out our reactants. So let's write out the reactants, and then I also like to identify the ions that the reactants contribute to their solutions. So we have two species that are being mixed here. We have potassium phosphate, and we also have magnesium chloride. This is where our chemical nomenclature again comes into play. We need to be able to know what the formula of each of these compounds are if we're going to understand what ions they put into solution and in what proportion those ions are put into solution. So we know that potassium phosphate is K3PO4 solution because we have memorized the polyatomic ions, right? And we have a phosphate polyatomic ion here, which has a -3 charge. Potassium, being a group 1A metal, has a +1 charge. So we need 3 potassiums for every 1 phosphate to create a charge-neutral compound. This is one of our reactants. Okay, what are we reacting this with? So the other solution that we are mixing with, so potassium phosphate is mixed with, is a solution of magnesium chloride. So magnesium is a group 2 metal, which means it has a +2 charge. Chlorine is a halogen, which means when it's ionized, it has a -1 charge. So I need 2 chlorines for every 1 magnesium in order to create a charge-neutral compound. So MgCl2. And I would like to identify, based on these formulas, what kind of ions are going to be put into solution from each of these reactants and in what proportion. So potassium phosphate, I've got that potassium plus ion, and there are 3 of them. And I also have my phosphate polyatomic ion, PO4, with a -3 charge. Magnesium chloride, this is my magnesium 2+ ion, and then I have 2 chloride ions, and these are the ions that are going to be mixed and undergo eventually at some point a double displacement. So step 2, perform the double displacement. And I always like to think about double displacements in general, but in aqueous reactions as being our cations getting new anions or swapping anions with one another. So I know that I have potassium cations in solution and phosphate anions in solution from potassium phosphate. I've also got my magnesium ions and my chloride ions in solution from my magnesium chloride. So if I'm going to look at this double displacement, I am going to need to associate my phosphate anion with my magnesium cation now, and my chloride ion will now be associated with my potassium ion. So this is the double displacement that is going to occur. And our third step is to create our charge neutral product compounds. Meaning I need to couple potassium and chloride and magnesium and phosphate in whole number proportions that make the total amount of positive charge in the compound equal and opposite to the total amount of negative charge. So let's look at potassium chloride. So this is going to form. Potassium has a +1 charge and chloride has a -1 charge, meaning if I were to need to make a neutral compound that is composed of potassium and chloride ions, this would be KCl in a 1-to-1 ratio. And then I now have my magnesium 2+ cation and my phosphate 3- cation. This one is not so straightforward, right? It's not a 1-to-1 or it's not a 2-to-1. So always when you have numbers that are not direct multiples of one another, we are going to look for whole multiples or the lowest common multiple between both. So the lowest common multiple of 2 and 3 is 6, meaning that I'm going to need 3 times the magnesium and 2 times the phosphate. This will give me an overall +6 charge, and this will give me an overall -6 charge. So I'm going to put together Mg3 and then phosphate in parentheses PO4 2, and this is in a 3-to-2 ratio. That was our third step. Fourth step is to write out our balanced chemical equation, hereby referenced as our molecular equation, because what we do in this full equation is we are showing every compound in their undissociated form, even those that are aqueous. So we had potassium K3PO4 solution reacting with magnesium chloride solution to form, we had potassium chloride, that is what we identified above, and we don't know the phase of this yet. And then we also have magnesium phosphate, whose phase we don't know yet, meaning we have not identified which of these products, if any, are a precipitate using our solubility rules. So let's balance real quick. On the left-hand side, I have 3 potassiums, whereas on the right-hand side, I only have 2 or 1. So I need to triple the amount of potassium chloride. And in doing so, I have also now tripled my chloride. So going on to my left-hand side, it doesn't look like I can easily get triple chlorides, so how about we look at something else? This here, my product compound, magnesium phosphate, is where things get kind of weird, right? This is where I deviate from like a 1-to-1, 2-to-1, 3-to-1 even ratio in my chemical subscripts. So how about I do magnesium first? I've got 3 magnesiums over here, so if I triple my magnesiums, then I am going to be balanced in that respect. Okay, phosphates. I have 2 phosphates, so I'm going to double the reactant compound containing phosphate, which is my potassium phosphate. And when I double my potassium phosphate, I'm also doubling the amount of potassium, so I now have 6 potassiums on the reactant side. So I need to multiply my potassium chloride product by 6. And in doing so, I have also multiplied the quantity of chlorine by 6. But notice on the reactant side, we have 3 magnesium chlorides, and each magnesium chloride compound contains 2 chloride ions. So we have a total of 6 chloride ions or atoms on the left-hand side or reactant side of our product. All right. Next step. Use solubility rules to identify any precipitates, PPT, formed. So writing 2K3PO4 aqueous with 3 magnesium chlorides. This is reacting to form 6 potassium chlorides and 1 magnesium phosphate. And now we need to reference our solubility rules in order to identify which of our products, potassium chloride or magnesium phosphate, is one that might potentially form a precipitate. So if I'm looking here at my chlorides, I do have a rule for chlorides. All chlorides are soluble except if we have silver, lead, mercury 1. And if you notice in this compound, it is chlorine, not with any of those exceptions. Additionally, we also have our universally soluble potassium cation. So we know that potassium chloride must be fully soluble, meaning it is in its solution form. It's going to fully dissociate into its respective ions when dissolved in water. Okay, but what about our other products? So I don't see, looking over here, at a rule for magnesium, but I do spy a rule for phosphates, which I certainly have in my product compound. So all phosphates are insoluble unless they are coupled with one of our universally soluble cations. And here we do not have either potassium, sodium, or ammonium. We have magnesium. So we need to follow the rule that all phosphates are insoluble, meaning that this will not dissociate into ions in solution. Rather, we will see this form as a precipitate or a solid that crashes out of solution. And again, let's just practice what this might look like in solution. So we've got our pre-reaction conditions, and then we have our post-reaction conditions. All right, let's make sure that we are in our pre-reaction conditions, putting in the proper amount of ions in their correct number of ratios. So if I dissolve 2 units of potassium phosphate, I create 2 times 3 or 6 potassium ions. And then I create 2 phosphate ions. And then if I have 3 magnesium chlorides in solution, I'm going to look at three magnesium cations being put into solution, and then 3 times 2, which is 6 chloride ions. And as a result, we are going to form product compounds, potassium chloride, which is a result of the association between our potassium and our chloride ions. Notice we do in fact have 6. But because these are aqueous, I'm just going to leave them in their ionic form. And then if I look at my magnesium phosphates, I need 3 magnesiums per every 2 phosphates. So I've got 1, 2, 3 magnesium and 2 phosphates there. So this is going to create solid. Magnesium 3 phosphate. Which is our solid insoluble precipitate. Okay. So in our next video, we are going to discuss one of the first ways that we can represent a chemical equation beyond just our balanced molecular equation for reactions that occur in solution. And that is by looking at what we call a complete ionic equation. So I will see you in our next video coming up next.